In this video we discuss how the ionization energy of an atom changes as we move across the periodic table. Okay, first let's define what the ionization energy is. The ionization energy is simply the energy that it takes to remove an electron from any atom in the gas phase. Alright, so this is the process. You remove an electron and then you form a positive ion. The energy to produce this process is what we call the ionization energy, or the first ionization energy, because you're just removing the first electron in the atom. Yep. Now, the variation of the ionization energy across the periodic table is as follows. The ionization energy increases as you move from the bottom to the top of the periodic table in a group, and then it also increases as you go from left to right in the periodic table. Now, the reasons for these trends are very similar to the reasons that we have used to explain the variation in atomic radii across the periodic table. Okay, so in a group, it's fairly easy to understand. Again, if we take the alkali metals as an example, okay, the electronic configurations are going to be helium, and then 2s1, and then the next sodium is going to be neon, 3s1, and then so forth. The next one will be potassium, that will be a 4s1, okay, with argon, and then as follows. So what you can see is that the last electron, okay, and this is the one that gets removed when you actually ionize the atom, right? Notice that this electron is always in an ever-increasing larger orbit, in a wave function that extends further and further away from the nucleus. Even more importantly than that, what happens is that as you go down the periodic table, okay, what happens is that the amount of electrons that you have in between the nucleus, okay, which is positive, and the last electron that you want to ionize, that one right here, okay, here you actually have an ever-increasing larger number of electrons as you go down the periodic table. Okay, so what happens is that the interactions between the positive charge in the nucleus and that last electron that you want to eliminate to ionize the atom, right, those get screened very efficiently as you actually go down the periodic table. And what that means is that as you go down, this ionization energy becomes increasingly lower, right? So that electron becomes easier and easier to remove. Okay, so that is the explanation for the variation across a group. Let's try now to understand the variation across a period. Okay, so again, the argument is exactly the same as the one that we actually have for atomic radii. And the idea is that as you go from the right to the left on a period, okay, you're actually increasing the effective nuclear charge felt by the electrons that are in that atom, right? So an atom that is right here is going to observe a larger effective nuclear charge per electron than if you are right here. Okay, so those electrons will be much more attracted to the nucleus than those right here, right? And that would mean that it would be much more difficult to eliminate, and the atom will be much more difficult to ionize. So that's why the ionization energy grows from left to right. Now, there are a few exceptions to this that we can review here. For example, we expect that as you go from beryllium right here to boron, the ionization energy should increase. But what we actually see is that it decreases very slightly. Let's try to understand why that is. Okay, so let's discuss here the case of beryllium and boron. Beryllium has an electronic configuration of helium, and then 2s2, and then boron has an electronic configuration of helium, 2s2, 2p1. Okay? Here you have 4 protons in the nucleus, here you have 5 protons in the nucleus. Now, something that is very important is that the electron, the lone electron in p orbitals of the boron atom, is very well screened by the 2s electrons, right? So if we draw this orbital diagram, that will be boron. Here you will have the 1s orbital with 2 electrons. Then you will have the 2s orbital with 2 electrons, which has a node in the middle. And then you would have this 2p, we're going to call it a 2px, electron with 1 electron. Right? The fact that these electrons tend to be in between the electron in the 2p and the nucleus, right, is going to mean that that electron is very effectively shielded from the nucleus. Right? And what that would mean is that, well, this ionization energy is a little bit lower than what we would expect if those electrons were in there. Right? So that is what causes the decrease in the ionization energy as you go from beryllium to boron, which is opposite to what we generally expect. Okay? There is another exception there in the second row, and that is that as we go from nitrogen to oxygen, okay, there's also a tiny little decrease in the ionization energy. And again, the reason for that is we're going to explain using electronic configurations. Okay, so if we erase this and rewrite the electronic configurations for these two atoms, that is going to be 2s2, 2p3, and then here we're going to have 2s2, 2p4. Okay. When we look at the box electronic configurations for the valence electrons, you're going to have here the 2s, 2p, and then 2 electrons right there, 1, 1, 1. And then for oxygen, you're going to have 2 electrons right here, and then the 2p, 4 electrons, 1, 2, 3, 4. Okay, so notice that the main difference here between oxygen and nitrogen in the electronic configurations is that the last electron necessarily has a wave function that is already shared by another electron, right? The language that we use for this is that the electron occupies an orbital that is half full. Right now you're going to have two electrons that are going to be in the same region of space, and even if they have antiparallel spins, which they should according to Pauli exclusion principle, there's going to be quite a bit of electronic repulsion. Right? So the repulsion between that electron, between these two electrons that are in the same region of space in the same orbital, okay, is going to mean that eliminating that last electron is going to be a little bit easier than we would expect, say, in the case of nitrogen, right? In nitrogen, you have that this electron is not repelled too much by these two other electrons because they are in different regions of space, right? Those two p orbitals are perpendicular to each other, which means that while there's some repulsion, it's not as large as if you actually have the electrons in the same orbital, right? So again, that increased repulsion between that last electron and the previously available electron in that orbital is going to mean that as you move from nitrogen to oxygen, the ionization energy, instead of increasing, is actually going to decrease a little bit. Okay, so there are some exceptions to this general trend that the ionization energy grows up in the as you go from the bottom to the top of the periodic table and to the left to the right, and those exceptions actually only occur across a period. Okay, we have seen a couple of examples as we go from boron, from beryllium to boron and nitrogen to oxygen, and again, all those seem to be related to electronic repulsion.